Okay, well, in this video, we're going to be taking a look at this table here that kind of acts as a summary of all the different things that we've seen in this section. Now, right off the bat, you'll notice that in this table, I kind of include some possible equation forms for the different quadric surfaces that we've talked about. But actually, I want to immediately discourage you from attempting to try to just identify the different quadric surfaces by possible equation structures. I think that that is the wrong way to go about things. You will make life so much more miserable for yourself. You won't remember things in a month from now when you need to. And the better approach is to think about the different sorts of trace curves, or how we imagine viewing the object from different perspectives. That's going to be so much more useful. Okay? So I would really encourage you, don't memorize the table. It can be maybe a good launching off point if you need to try to type something into the 3D plotter so you understand what something looks like again, but don't try to memorize these forms matched up with the names. Try to understand where the names come from and how they relate to the trace curves. Okay. If you were to take a look here at example number 7, these are going to be some extra sample problems that we could imagine doing. And these would be sorts of problems that you could imagine seeing on a homework or on an exam or something like that, right? Where I would just simply ask you, hey, here's an equation. Could you give me a sense of what this particular quadric surface looks like? And again, I think the approach is exactly the same that is what we've taken in all of the other problems here. So let's take a look at each of these together. If you'd like, you might want to try pausing the video right now and giving these a shot yourself. And then when you unpause the video, you could see me kind of work through the solutions as well. So I'll let you choose what you feel like is your best approach. Of course, there is worksheet problems associated with this section as well. All right, so let's go ahead here and try to figure out part A. What in the world is this quadric surface? So again, I'm going to go ahead and I'm going to think about what happens as I view this looking down the x-axis. If I was to do that, notice I'm going to get some sort of structure like a y squared over 4 minus a z squared over 2 is going to be equal to 1 plus some number that gets plugged in for x and then squared. So this here is a hyperbola. When I view this down the y-axis, what I'm going to see is I have minus an x squared minus a z squared over 2, and then a 1 minus a y squared over 4. Now this doesn't seem to resemble any of the conics that we had talked about, but if I multiply both sides by a -1, then I can actually see that this is really similar to the structure of an ellipse. Okay, so I might have to come back to figure out how those ellipses behave if it's the case that I also end up with a hyperbola for the other direction, that final perspective. Because remember, whenever I have two hyperbolas and an ellipse, I'm dealing with something like a cone or a hyperboloid of 1 sheet or 2 sheets. Okay, so let's take a look from the z-axis. Notice here I'm going to get something like y squared over 4 minus an x squared is going to be equal to 1 plus a z squared over 2. And yep, definitely here I'm ending up with a hyperbola. So I'm really going to need to go back to those ellipses and see how they behave. Are there numbers I can plug in for y that would make the ellipses ever not exist? Do the ellipses ever shrink to a point? Like, what happens here? Well, one thing I could notice is that definitely these ellipses shrink to a point. They do indeed shrink to a point. And that specifically is going to happen here if y is plus or minus 2, right? If y is plus or minus 2, over here I'm going to get 1 minus 1, that's a 0. My ellipses have shrunk all the way down. Okay, so that means there's no way this is a hyperboloid of 1 sheet, right? It's got to be one of the other options. So let's see if my ellipses ever stop existing, right? That would be good to know. If they ever stop existing, that is, if I can ever make this side turn into a negative number for values of y, then that would mean that I must have a hyperboloid of 2 sheets, which had that kind of gap, that empty space where no solid existed. I can definitely see here that they do stop existing. Those ellipses do stop existing specifically when I think when y is between -2 and 2, right? If I plug something like a 1 in for y, I'm going to recognize I get like 1/4 minus 1. That's going to be like a -3/4 over here. So I can definitely see that my ellipses are shrinking to a point and they do stop existing. So this here would be considered a hyperboloid of 2 sheets. Okay. All right, well, let's look at the next one. The next one looks a little strange because I have some shifts that are happening in the graph. That's what's happening here in the parentheses. This is going to shift the entire solid 3 units in the x direction and shift the entire solid maybe 1 unit in the y direction. But ultimately, it doesn't change anything about what happens when I try to view this down particular lines of sight, or when I try to look at the solid from different perspectives. So again here, if I was to look down, say, the x-axis, if I was to replace x with a number, notice that what I'm going to end up with here is y minus 1 is going to be equal to, I'm just going to say, some number squared over 1 plus a z squared over 2. Notice I'm just kind of saying that whatever number I plug in for x, when I subtract 3 from it, I just get some other number. And overall here, I think that this shape would produce a parabola. Okay. If I go down the y-axis, or look at it down the y-axis, I'm going to get some number over on the left side. And then I'm going to get an x minus a 3 squared over 1 plus a z squared over 2. And I think this has the general shape of an ellipse. And finally, if I stare down the z-axis, I'm going to end up with a y minus 1 in x minus 3 squared over 1, and finally plus a number squared over 2. Again, I think that this here resembles a parabola. So remember that this is going to be that kind of basic shape that looks like this. Now, of course, it might be rotated. You know, it's totally possible that maybe this shape like opens off to the side, or it points down or up, or I mean, it can be reflected or rotated in a lot of ways. So I have some sort of shape like this floating out in space. That's the important part for our purposes. And remember that this here is referred to as an elliptic paraboloid. So again, even though I have these basic forms up here in the table, I'm not using those to try to go through and determine what these things look like. It can be done, but it's a really bad strategy, so I'd highly advise against it. Hopefully what we're doing here seems to make sense. It is a thought process that will kind of pay dividends later on in the course, and so I encourage you to try to keep practicing with it. And of course, if you happen to have any questions, let me know.